Oh, well. Okay. So one topic that we do need to go through is the sources of electric potential. So we've talked about this idea of electric potential. We've talked about how if you have two charged particles and they're separated by a certain distance, we can talk about the electric potential energy that one has relative to the other, right? Does this sound familiar? It's been a weekend, so I want to make sure this is okay. So two charged particles. I've got like a positive charge here, and I've got another positive charge here. And this one has some electric potential energy relative to the other one. And we could quantify that amount of potential energy, yes? Okay? How do you quantify it? Did you say you can't? Yeah, but I suppose, yes. So K, what?
K, Q, Q over R.
And what did you want to do? QED. So we have to just kind of keep in mind what's going on here. So this is 2-point charges, right? In order to use this version of the equation, the QED version, you have to know the electric field. You can do that. You can find it, right? Because that's KQ over R squared, and then things cancel out and you get the same thing. Are you with me there? Is that okay? Do you want me to back up and say that again, or are we okay? Okay? All right. So you've got QED, or you've got this thing. You can find the potential energy. If this charge wasn't here, this one over here still is, it's kind of funny to say giving off, but there is still an electric potential at this place due to this charge. Is that okay with everybody? How do I quantify that electric potential at that spot?
By dividing out the second.
Yeah, you got to get rid of that other Q, right? So you're going to divide by Q, divide by Q, divide by Q, and the voltage associated with that spot, the voltage, the potential, right, the electric potential, all those fun names, at this spot is equal to the strength of the electric field here divided by the distance, or is KQ over R. It's the same thing again. So you can create an electric potential by having a charged particle. Yay! But when we start to get into the topic of like a circuit or something like that, it's not like you're just going to hold a charged particle there and be like, all right, let me have a potential, right? Like that doesn't make sense. That's not practical. It does. I mean, it's not how we do it. So we want to make sure that we know how one might get a potential difference. Okay? Here's the deal. Anytime that you separate charges, anytime that you take two charges and you pull them apart, you are creating a potential difference between them. Okay. We did this on the very, very first day that we started talking about electricity. Remember we had that rod and I had that fake bunny fur? Okay? Let me say this real quick and then I will answer your question. Is that okay? When we did that, we were pulling charges from one thing onto the other. And in doing so, we're creating a potential difference.
What if it's equal charges?
What do you mean?
Like two positive charges would be equal magically separated by a distance.
There's still a potential difference between them. Because, so let's back up for just a second to explain why that's true. So let me make sure I understand what you're saying. You're saying there's a positive charge here that's 1 coulomb of charge, and there's another 1 coulomb of charge here?
Yeah.
Yeah. So there is still a potential difference that's established because, if we back up, there's electric potential energy that charge has, or that object has relative to that one. Does that make sense?
Yes.
Electric potential energy is the blue stuff, right? So U is equal to KQQ over R. If there's potential energy that this one has relative to that one, then there has to be a potential difference between them.
Yeah.
Is that okay?
Yeah.
Okay. Was there hand? Okay. So we can do that with charges, but generally we don't use that. There are two different ways that we do this most frequently. One is kind of what I described before. That's mechanical separation. So that's what we do with the bunny fur and the rod. This is exactly what you do when you're tormenting your siblings, right? You wear those wool socks, and you go like this, right? You're separating charges, and really what you're doing is that you're putting yourself at a higher potential. You're collecting a bunch of charge on you. You are now at a higher potential than the surroundings. Are you with me there? Okay. You walk up to your sibling. Hey, how's it going, right? You've got a whole bunch of extra charge on you. Does that charge really want to hang out just on you?
Share the love.
No, it doesn't. You know this, right?
What?
Oh, you want to share the love?
Yeah.
Yes.
Wait,
Yes.
what?
I thought you said sure. And I was like, no, not really, right? You have a whole bunch of charge, whether it's positive or negative, you've got a whole bunch of charge. When you shake hands or touch or whatever, you know what I'm saying? Then that charge is going to spread out because those charges want to go from a high potential to a low potential. Okay? Just like the frog wants to go from a high gravitational potential to a lower gravitational potential. It's the same deal. This is just with electricity instead. We okay?
We're saying potential, not potential energy, right?
Right. Because, so the frog has potential energy,
Yes.
but there is a gravitational potential that exists here that is different than the gravitational potential here.
Yes.
Because gravitational potential is dependent on both, in this case, the acceleration due to gravity and the height. Yeah.
Okay.
Is that okay?
Yeah.
Okay, okay. So, we can establish this source of potential based on mechanical separation. We can also use chemical separation. We're not going to go into exactly how that works. You can take chemistry for that, okay? But a battery, okay, is a very, very common source of potential difference, okay?
We have an IA or
Do you guys know how batteries work?
Oxidation, rejection.
Maybe learned sometime, but
Yeah.
Yeah.
There's some sort of reaction, right? Some sort of oxidation, blah, 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 whatever. In your book,
Salt bridge or
it makes me kind of want to, like, it makes me a little crazy because they're like, we don't want to play with chemistry at all. And so they draw this, and I don't like it, but I just want to make you aware of it. They show these little charged particles as going up a little escalator. I'm like, they don't really go up, there's no escalator in here, friends. But there is a chemical reaction that occurs inside the battery, right? That separates the charges.
It strips electrons from one thing and puts them on the other.
There you go. So you've got a bunch of, right? So we're literally separating the charges so that one terminal of the battery is at a higher potential than the other one. What's the potential difference between the two terminals of this battery?
About 1.5 volts.
Yes, it was manufactured to be 1.5 volts. I've been using it for a year, so it may or may not be quite at 1.5 anymore, but that's what we're setting up, okay? So this chemical reaction causes positive ions to, I don't want to say go to, that sounds wrong. What do I want to say, AJ? What's the word I want? I need a verb.
Transfers.
Sure.
It's reduces.
Yeah. I'll say transfer. To one side
Sticky wall.
and negative to transfer to the other. And in doing so, okay, we get two sides with charges that are separated. The reaction requires work to be done. If we're going to change energy, work has to be done, right? Delta U, that's our energy, or our delta U is equal to negative W. If I divide by Q, okay, this gives me, this work provides me with a potential difference. Now, do you remember when I first was telling you about potential difference and electric potential and and voltage, and there were 5 names, and or was it 4, and I told you there was a 5th, or there were 5, and I told you there was a 6th? Today we're going to get to the 6th. When we're talking about batteries, okay, we talk about this ideal situation, the ideal situation in which this battery is doing its chemical reaction. The potential that we have there is also known as EMF. Okay? EMF is marked with a little script E. Okay? It is the theoretical potential across the terminals of a battery. So the trick is that a battery is not perfect. There is some internal resistance that exists in this battery. You're like, I haven't heard that R word before. Well, maybe you have. But just what I'm trying to say is it's not perfect. Okay? And even though it's supposed to be at exactly 1.5 volts, it's not. It's actually manufactured to be a little higher so that when you take this with your voltmeter, you can actually measure it as it is 1.5 when you buy it. Okay? The EMF is a term that I strongly dislike because of what EMF stands for. Yes, it stands for electromotive force. Here's the trouble with that name. Electromotive force would imply, so this is like an adjective and this is the noun and it's a force, right? It's not a force. Okay? So even though it's called electromotive force, it is not a force. Electromotive force just means, for our purposes, it just means voltage. Okay? This was a question that came up at some point during Science Bowl. I remember going, oh man, we're going to talk about that in 5 days. Yes. Electromotive force is voltage. That's all you really need to know. Okay? You can call it EMF. And in my experience, they use these terms interchangeably. Okay? They don't mean exactly the same thing. And so if you talk to an electrical engineer, they're going to be like, they're not quite the same. But for our purposes, they're pretty darn close. So for our purposes, they are the same. Okay. Issues, questions, concerns there? One more little thing. Well, I guess 2 little things. I kind of implied this, but I just want to make sure it makes sense. So the terminal voltage, what do you think that means?
Maximum possible voltage, where all the potential and all the potentials on one side.
Between the terminals and
Talk to me again. What did you say?
It goes wrong.
But talk to me. I want to process what you said, though.
Maximum voltage.
The voltage, right? From one side to the other. That's really what it means. Yeah, yeah. So it's not like, not terminal like a terminal illness. It's terminal like from one terminal to the other terminal. Yeah. So the voltage that one would measure on a battery, V, will always be less than the actual EMF inside the battery. Question?
So then is like the length of the battery important? Because like the positive wants to go to the negative, the negative wants to go to the positive. So if they're farther apart, the positive and negative terminals are farther apart.
No.
Would there be greater?
No, it's all chemical reaction side, right? Because from a physicist's perspective, all I want is all the positive to be here and the negative here. And let's be really clear, it's not like this is like filled with protons and electrons, right? We get that. There's a chemical reaction that's going on inside the battery that is causing those charges to split.
Yeah.
Okay? The size of the battery does matter, but it's not a physical size about like if it's longer, then it's going to have a higher potential. Okay? AA batteries, AAA batteries, D cells, C cells all have a 1.5 volt potential difference.
it's just that D cells last longer.
D cells last longer because they've got more chemicals to do more chemical reaction. The reason you would use a AAA battery, those are the little tiny ones, right, is because you're using a device that you want it to be small, right? You don't want to have, like, your remote control have to have these things, like, sticking on the side of it. That's just not efficient, okay? What's that?
That's like your old cast, the ones that actually use actual batteries.
Right, exactly, yeah, yeah. Does that make sense? Is that okay?
I guess. But this is related
Yeah, no.
to voltage and the differences. Isn't it? I guess it's changing potential energy over Q, but
Right, okay, so like the equations and stuff that we were playing with before,
yeah.
that's all electrostatics. This is a chemical reaction. That's a fundamentally different thing.
Okay.
So when we get into like capacitors, which we're going to get to soon, then that distance does play a part. But inside this, the only reason this one's bigger is because we want more chemicals, so more chemical reaction, so it lasts longer.
Yeah.
That's all. A 9-volt battery, you know the square ones with the terminals on the top? Okay? It's 9 volts, oh duh. If you've ever taken one apart, and I would not recommend it because it's kind of gross and it's kind of dangerous, but like if you happen to see one that's undone, okay, really all a 9-volt battery is, so battery actually means that it's a pile, and each individual piece is just 1.5 volts. It's like this little, if you look at it from the top, well, if it's 9 volts, how many 1.5 volts would that be? Right?
Oh God.
Do you understand what I'm saying?
Yeah.
I know, right? I'm asking a lot.
So many subjects at one time.
What is this? There are actually just 6 1.5 volt cells inside a 9-volt battery. That's all it is.
You can actually take it apart and use those as AAA batteries.
Okay, I'll do that next time I want.
Next time you're looking for a AAA battery, right? Like, man,
Dang it,
Let's-
all I have is-
does this happen a lot? Yeah.
Okay,
Okay.
I mean, like if you need AAA batteries for something.
Would it like fit?
Yeah,
They fit?
They're the right
They're
size.
a
Oh,
bunch
they're
of
right- oh,
AAA
okay.
batteries.
More
Just in a
importantly, have
package.
you ever taken an 9-volt and put it on your tongue?
Yeah. I had a boss I used to work up at Iowa State, and my boss,
Is that how you tested it?
whenever there was a new person coming into work, he's like, "Hey, would you test this battery for me?" It was so mean. Don't do it. It hurts. Don't do it. Can you put batteries?
Thank you, Jack.
Can you put more than one battery in something at a time?
Yes.
You what?
Yeah, obviously you can, right? Like a flashlight. Oh yeah.
Oh.
You put 2 batteries in, so if I stack the batteries like this is not a surprise. You guys have all put batteries in flashlights before,
That's how
right?
you do it? Oh God.
I know, right? It's kind of
Same direction.
I always assume
It's
when you put them
confusing.
in, they just combine to make one battery.
they like fuse together, and then as soon as you open it, then it breaks apart again.
What?
Jack, my friend, I'm not trying to break your heart.
Show me what?
If you stack like 15 9 volts and touch both ends, like, it would be dangerous.
No,
You're touching both. You touch
because the current's not going to be high.
Yeah, but it's not 9 volts, but if you have like 200 volts or something.
Why are we trying? Okay.
Let's do it. That's our lab.
It's not the voltage
It's
that
right.
kills you.
It's the current. Exactly. It's not the voltage that kills you, it's the current. So, the thing that I wanted to just point out here, and this should be something that's obvious to you, except maybe not Teresa because she seems to be blown away by this, is that voltage
I'll give you that.
in series adds. What do I mean by that? I mean that if you take 2 batteries, that's 1.5 volts, and another one, 1.5 volts, then the terminal voltage here would be what? 3 volts. I mean, I know it's wild and crazy. And I really don't want to imply that if this wasn't obvious to you that you're not smart. I don't mean that at all. But I think that is an okay statement, right? If you put them in positive to negative, so you put them in the right way, then you will add. If you put them in this way, then these 2 are both positive, these guys are negative, and then you don't have a potential difference anymore. Do you see what I'm saying? Okay? Right?
I've been doing it wrong this whole time.
So here's the deal, friends, is that I can go through this really fast, and I'm fine with that, but I don't want you to say to me later, "Oh, I didn't know that." You never, right? Like, don't tell me that, okay? Because this stuff really, it does kind of add up and matter, okay?
Upside down pyramid thing that Pepper knows talks about.
What's that?
What? it's that upside down pyramid thing that Hubbard always talked about.
Everything is cumulative.
Yeah, it's like you're just more and more, and I was like,
It's true though. It's true though. No pressure. Okay. Questions about sources? All right.
Where's ground when you have two batteries?
Yes.
Where?
Yes. You can set ground wherever you want it, right? So like generally ground is going to be at the low. Is that what you're asking me?
Yeah. Like, how do you end up with negative voltage? And now where's ground? But
So okay. So no, I'm not trying to be snarky. I want to point out a couple of things. So he's saying this word ground, and we haven't really talked about this. So let's make sure that everybody understands. What does he mean by ground? What does that mean? Yeah. So to ground something literally means, like, where does it come from? It means that once you've separated these charges, you've got a bunch of stuff that's a high potential. To ground it would mean to connect it to the earth. The earth is a humongous charge sink because there's not going to be, like, you can throw a bunch of charge on it, it won't matter, right? There's so much stuff there, it doesn't matter. So to ground something literally means to connect it to the ground. Okay? So if you look at an outlet, the funny shaped plug is ground, which means that it is actually connected from that plug down to the ground, electrically
Is there just
connected.
like a chunk of metal stuck in the earth?
Yeah.
What do you mean?
Is there like
A wire?
You
Yeah.
stick a wire in the ground?
Yeah.
Oh, okay.
Yeah, like literally that's what they do. Okay? I mean, there may be a little bit more to it from an electrician perspective, but
okay, well, it's like a wire in the ground.
but actually, yes, that is what they do.
Okay.
Yeah. So, no, I don't mean that, but I'm just saying, like, that is actually what's happening. Okay? When you talk about something being at a high potential, so if you have these two batteries and nothing is grounded, what is ground? So ground is usually a zero potential, right? But there might not be a ground here. This might be at a higher potential than ground. And that's okay, we don't know. Because just like we had when we had gravitational potential energy, where you get set H equals 0 wherever you want, same deal with this stuff,
Okay.
right? So all that we know is that this is 1.5 volts higher in potential than this. If we connect this to the ground, then this is 1.5 volts higher than ground.
Okay. So, how do you get like something that's lower potential than ground?
You have negative potential.
Yeah. How do you do that?
Well, if
Have
you
negative
said-
charge.
If you said like the top then was zero,
Like-
then you would say there's negative 1.5 volts.
Right.
So I connect the top of the battery to ground instead
Yeah.
of the bottom.
Yeah. Yeah. Is that okay?
Yeah.
Yeah. Okay, go.
What movie is the voltage star?
Is it what?
What movie is the
I can tell that this is a terribly relevant question, but I don't know the answer to it. Nathan, could you tell me?
Terminator.
Ah. That's the best you were going with.
Wow. Wow. Okay. On that note, shall we move on? Yes, please.
Wash your hands. Double A battery with a leather jacket on. Movie.
Yeah, you guys can work on that. All right. Okay. Shh. Come back to me. Thank you. All right. So last time we were together, we were talking about potential and how it's related to electric field. And we went through all of this stuff, and I don't think we did a couple of problems with this yet, did we? Did we do a couple of problems with graphs?
I'm not good.
No.
Not graphs? Okay,
There's
that
a
means we
homework,
knew.
though.
What's that?
There's one in the homework.
Oh, that's fun. Yay, you're welcome. You sounded excited about that. That's why I said you're welcome.
Oh, yeah, no, it wasn't too bad. Like, it was just that, yeah.
All right. Here we go. So these, my friends, are really not hard if you know the relationships between potential and electric field. Okay? So here's the first one. These are from your book. Okay? This is example 29.1.
0.2.
Nope, that's just figure 29.2.
Okay.
It's question 29.1. There was just a picture earlier in the chapter that was called 29.1.
Example one? Okay.
Example 29.2
That was 29.1.
or 29.1. Sorry, Teresa's a problem today.
It could be 29.2.
Right.
I helped you so much this morning, though.
Right.
Oh, okay.
You did. All right. It says a graph of the electrical or electric field is shown. The x component of the electric field versus the position along the x-axis. Find and graph the voltage with respect to x. Go. This is not super tough, but I do want you to go through it. Once you got an answer, check with your neighbor, see if they agree.
Yep, it passes through the point 001 500.
0, 0.
1 500.
Is it concave up or concave down?
Up.
Oh, wait, 'cause it's a parabola. Down.
Parabolas can open up or down.
Well, but I mean, it opens up.
No, it's down.
But no, this is just the integral of a line with positive slope. That's the.
But no, but it's negative.
Oh yeah.
Negative integral, right?
Tricky.
Oh, oh, oh.
That's right. Negative.
So,
Oh, but then I mean, it starts at.
So it starts at 0, 0, right?
Yeah.
And where does it go through?
dx.
1 negative.
One negative.
2 negative
2
And then you divide through by q.
1,
Right, because
2,
q's constant, you can do that.
Yeah.
negative 1,000,
Oh,
And then
negative 2,000.
electric force divided by q. is
500
electric
and
field.
1,000.
Electric field.
I'm asking.
500 and 2,000.
Oh, okay.
500 and 2,000.
Well,
What?
I mean, she's gonna put it at negative 500.
Somebody go up and do it. Yeah, you aren't using good word. Like you're not helping me. Help me out.
The points.
Maybe
Jack,
you
come
should
here.
go up and do it.
Me.
Graph it. You can get help from your peanut gallery.
Where's the eraser? Oh, it's already on erase. What?
Flip it over like a pencil and then you can erase it.
Oh, fancy. Okay. Now what? Right or
Yeah, then click on the red pen maybe.
that one?
There you go. Yeah.
Okay.
But
Is that right? Wow. You know, we have to sacrifice.
All right, come on, guys.
Let's run
Stay
this one.
focused. Help each other out.
Right? Is this Nathan? Do you agree? So then you got that point, and you got that one, and it's like, ooh, I don't know. I'm not the best grapher, but.
Okay. Let's take a look. Do you guys agree with that graph?
Move that point. Now it intersects that point.
If I was grading this this problem, would I give you full credit for that?
No.
What? Why not? What's wrong?
Didn't label the keys.
Well,
Oh,
that
Lord.
too. Yeah, the scale doesn't make any sense to me. It's like some sort of crazy log scale or something. How about make it something that makes more sense?
What?
Add 1,000 to 1,500 in there somewhere.
Space them out so they make sense.
So
Move the
all right.
500.
Move the what?
Move the 2,000
Okay.
down.
Change the 500 to 1,000.
Yeah.
What? What do you guys? All right. I'm gonna do this my way.
123 billies.
C-stick.
Because you're up there, so you might as well, right?
Yeah.
Right. That's diagonally. I set the right trigger to attack.
That seems like a good plan to me.
Wait.
Wait,
I am, but
I just
physics won't.
realized they tell you that change in V equals
Yeah.
negative area.
Yeah.
Boy, y'all paying attention. And then we got. Ooh.
There you go.
Boy, I cannot hit that point. Sure.
That looks better to me. Is that okay with everybody?
Yeah.
Okay. Nice job, Jack. Give him some applause from somebody there. All right. Try this one. This is example 29.4. In your book. Below is a graph of electric potential in a region of space where the electric field is parallel to the x-axis. That matters. We'll talk about that in just a second. But for right now, go ahead and draw a graph of the electric field versus x. Can you do this?
Yeah.
Great. Do you need to see any of those numbers? Are they hard to read?
A little bit.
This one's 10, 0, and negative 10. This is all voltage. The other ones are 2, 4, 6, 8 in centimeters. Once you've got something, show it to your neighbors, see if they agree with you.
I got 3 different line segments.
All right, somebody ready to come up and draw for me?
Sure. That was good.
Go, EJ.
Let's start right there. I have to do math there. Yeah.
What's wrong?
Nothing.
Always put it right on the same one. Whoa.
Oh, it's negative. Ah, dang.
What do we do about those points? Like open dots, or you want? It always bothered me in we go through square waves and there's electronic dots here. Like even the oscilloscope would go out like that. It doesn't really make sense.
Yeah.
How do I erase it? Turn over.
There you go.
Oh, yeah.
How are we doing? Is that okay? Does that match what you were thinking? questions make you happy?
Wait, I went to 5 and I have to go to 4. Are you happy?
Abby, you doing okay?
I'm
Yeah,
sad
yeah,
because
awesome.
I'm
Teresa?
happy because
Yo.
I figured you'd yell if you're unhappy, is that true?
it's a vicious cycle.
Or like when we're in silence.
You'll let me know that you're unhappy, is that
Yeah.
true? Okay. All right. Okay, so we can take integrals, we can take derivatives, yay, go us. Sometimes we like to look at this stuff geometrically as well. I don't remember, oh, that's a picture that I don't want you to look at yet. So let's take another look here. So they kind of walk you through this in the book, but I really want to make sure this makes sense to you. So you know that forever I keep mixing up my parallel and perpendicular, and the reason for it is this idea of equipotentials that I get myself stuck on. So the word equipotentials is kind of nice, right? What do you think it means using your context clues and your word within a word skills?
Equal power. So it's like lines. So it's like lines in
That's
which
true. That's what's in the word.
potentials is equal. Right? So with those like lines.
So, okay. So, do you remember when you were in elementary school, where this all comes back to elementary school, when you were in geography class and you used to look at different kinds of maps? And one of the kinds of maps that you would look at was a contour map. Do you remember looking at a contour map? And like a contour map of Iowa is going to be really unexciting, but then you look at a contour map like maybe of Colorado, and western or eastern Colorado is really boring if you've never been. It's like more boring than Nebraska. What? But then if you look in western Colorado where there are lots of mountains, then you might see things that look like this, right?
No, I just like gravity. Like if you did equipotential.
These are gravitational equipotentials. That's exactly what this is. So tell me about, this is a gravitational equipotential map. So a contour map that you learned about in like 4th grade or whatever is really, I mean, I don't know why your geography teacher didn't say, it's really just gravitational equipotentials.
That is what I said.
That's what your teacher, or that's what you said.
I taught myself.
That's a contra.
No, that's what you told your classmates. Or-
Yes.
Yeah.
Goals, Peter. I don't know anything about this. I know.
Talk to me about this gravitational equipotential map that you've got here. What do you see?
Potential.
It's really steep at the bottom, like at the part down there.
Okay, why don't you raise your hands? Because I can't take all of this like random talking. It's driving me nuts. Go.
As you, like, whatever the thing is that you're
It's a mountain.
mapping, it's a mountain. Okay,
Sure.
so the peak is more towards like the south end of it, and its slope there is steeper than on the north side.
So like the slope on this side over here is
It's really
steeper
steep compared to,
than over here. How do you know that?
because the lines are closer together.
Does that make sense? Those lines are really close together, which means that because each of those circles represents what?
Change in altitude.
Like they represent equal.
Like a specific.
A certain altitude, right? So like a certain number of meters above sea level. And so from here to here is the same change in altitude as from here to here, right? So here it must be a pretty gradual slope, whereas here, yikes, it might be kind of scary. Nathan, you were going to add something. Are you sure? Okay, okay. Andrew, I thought you had your hand up as well.
No.
You sure?
No, I mean, you answered it. Because the lines represent equal height, so equal gravitational potential energy.
Right, right. And that's something that I do want to write down, so let's write that down. So each of the lines, hold on, let me write this down first. Represent a height, but what they really represent to us is,
The change in gravitational.
yeah, or a specific gravitational potential relative to sea level, right?
What does it say? Specific.
gravitational potential. Sorry, sometimes I just write little and then it gets weird. Nathan, what's up, hon?
This is a two-dimensional point charge, right? It's not, is it in three space or?
So this is a mountain.
Oh yeah, like.
Yes, but when we start to do
Well, I'm saying-
charge particles, when we start to do electric potentials, then they are in 3 dimensions.
So this is only on one plane, right?
Right. Right. So we're only drawing it on one plane, but you could draw it from any perspective. Yes. Generally, the things we're going to look at are going to be symmetrical, which will be nice, but not always.
So like if it's a point charge, there's just a bunch of circles, right?
Right. Concentric circles surrounding that charge. So let's do this. For electric, I feel like there's a lot of chatter right now. If you have questions, let's address them to the whole group, just so that we can have one learning experience. If they're not necessary, then don't include them. Thanks. So for electric equipotentials, if we have a single point charge, what are the equipotentials going to look like? Circles that are all where? Are all centered where? At the charge, right? So it's going to look something like this, and then like this, and these are supposed to be all concentric. And they're going to be evenly spaced. Go ahead, Nathan.
That's what I was gonna ask.
Yep, evenly spaced. Just for kicks, would you also draw the electric field lines for that charged particle? What do you notice about the electric field lines relative to the equipotentials? They are always perpendicular, always normal to the equipotentials. And that is super important. Okay? What's that?
Like a gradient.
Yeah, or something. So if you know how to draw electric field lines, this is just one more way that potential and field fit together, right? If you know how to draw the electric field lines, which you do, you can always draw the equipotentials because they're always going to be perpendicular to the field lines. Okay? So what if you have multiple charges?
Oh,
And
then
the
you give up.
equipotentials are just
You don't give up. Wrong answer.
It's gonna be like a peanut shape.
Yes, actually, you are exactly correct. I was going to pull this one out. So if you have something like this, if I was going to draw the equipotentials, what's that? What's that going to look like?
have
Peanuts.
a straight line through the middle.
So really, really close. So let's just think about this one thing at a time. Really, really close. What's the equipotential around this one going to look like?
Circle.
It's going to be a circle, right? But those concentric circles are going to start to get closer. And then out here, they're going to interact with one another, right? And so further out, your equipotentials, they always have to be perpendicular to those electric field lines. So they're going to be kind of circular over here.
There's one potential. This goes vertically all the way straight through the middle.
That's hybridization.
Yeah, hybridization.
Like this. Oops.
Eventually I got what that was.
Yeah. So that just net potential too, just like infinitely
All
the
4, 7.
I remember.
I'm thinking.
Yeah, it sucks.
Seems like it should, but I'm not positive. I don't feel like that doesn't feel quite right to me. But maybe, yeah. Yeah. Okay. Let's see. What else do we need to say? Oh, so I wanted to look at another little bit more specific situation. There's a picture in your book that has this as well, but I'm just going to kind of sketch it out. Generally, we draw equipotentials as dotted lines. So if I've got two equipotentials like this, that are just kind of set up like this. And I'm going to call this one V minus and this one V plus. So this one's at a higher potential. The one below is at a higher potential than the one above it. Okay? And I'm looking at a point here, point P, and looking at two possible displacements relative to those equipotentials. One possible way that I could displace this charge would be along the equipotential. If I have delta S, I'm calling it delta S1. This is kind of sticking with the way it describes it in your book. Okay? Delta S1 that is parallel to the equipotential. Well, if it's parallel to the equipotential, then we know that delta V equals what? 0, because it's not changing the potential, right? Okay? We know that there's no work done. We know that ES is equal to negative dV ds, so that means that is there any electric field in that direction? The strength of the electric field is just equal to the derivative of the difference in potential. Since that's 0, then this guy has to be 0. So when you're drawing electric field lines relative to potentials, this is why no electric field is going to go parallel to an equipotential. Okay. If you look at the piece that's going perpendicular, we'll call that delta S2. Okay. Perpendicular to the equipotential. E perpendicular is, well, it's negative dV ds, we know that, which is an approximation of delta V over delta S. Just undoing calculus here, right? So we're changing our potential as we go from here to here, divided by the distance that we're going to travel. That's like the opposite of our change, V plus minus V minus over delta S. In this case, delta S2. The reason I wanted to go through this process is to show you that the strength of the electric field, right, that's what we've defined here, the strength of the electric field is inversely proportional to the spacing between those lines. Okay? The stronger the closer the lines are together, the stronger the electric field. The bigger difference that you have. Okay? So E perpendicular is proportional to 1 over delta S. And the last little piece of that that's important to know, okay, is that the strength of E, or the direction, always points what we call downhill or toward the lower potential.
Delta is pointed from V plus to V minus.
It does. But the direction, because of this negative sign, the actual electric field line points the other way. Yes. Does that make sense?
Yeah.
Yeah.
So the dotted lines you drew would be like the contour lines that you would draw?
Correct.
Okay.
Exactly. So this is just like a really small or a really zoomed in picture from this.
Is it dotted?
Because generally when they draw equipotential lines, they draw them as dotted lines. The first ones I drew were solid lines just to kind of make a point of solid lineness. Okay. There's a picture in your book that did not get scanned in very well, but I would just recommend that you look at figure 2914, not example 2914, figure 2914 that is on, I'll tell you, on page 846, okay, that kind of puts this stuff together nicely. just to kind of keep it in your head. So that might be something good to look at. How are we doing? We okay? Okay. One more problem with this, and then we're going to move on. This is example 29.5. Example 29.5. It's figure 2915. And this is just kind of a sketch problem to kind of keep in your head how to work this. So we've got 3 equipotentials that are graphed on this centimeter by centimeter grid. The question asks you to estimate the strength and direction of the electric field at the points 1, 2, and 3 as shown. Show your results graphically by drawing the electric field vectors on the contour map. Okay. Make that a little bit bigger so it's easier to see. Go ahead and talk that through with your partners. How would we go about doing that?
Find the distance from the point to 0 volts.
So E equals the change in voltage divided by the distance, right? So in this case, you're going
1 centimeter.
1 centimeter and 50 volts. So what's that electric field strength?
5,000.
5,000? And then what about for 3? This is the one that you guys were discussing back there.
No, we're discussing.
Oh, you were discussing number 1?
Yeah, we're good.
So do you agree with what I said?
Yeah.
So what did you say on 3?
We just have the thing 50 divided by 0.015.
Which is equal to about 30.
Don't you mean 1 point something?
0 divided
Which is equal to about 3,000.
Oh, okay. I'm sorry. I wasn't listening.
3,330, I think.
So that's like 4,000-ish?
I think it's like 3,330.
About?
Yeah.
Whatever. It's close enough.
Because it's 333.
True.
3.3.
So many 3s. And then for E2, that one's going to be easier. Something like 25, right? 2,500. And then where do the arrows point?
Towards the up and like to the left.
Up and stuff.
Depends on
So something like this. And if that one is this long, so that's to answer your question, Jack, if this one is this long, then the one from 2 should be half of whatever that was. Whoa, hello. And number 3 is going to be in between. Something like that? Is that okay?
Yeah.
Yeah. Brian, how you doing? You sure? Okay. Last chance for questions on this stuff before we move on. I'm going to take the last 10 minutes to do like an intro to capacitors. Can we do that quick? Capacitors? Here we go.
Wait, quick question. Are we on schedule right now, or are we doing like?
We're a little ahead.
Okay.
So we are starting Wednesday stuff right now.
Okay.
So we're 10 minutes ahead. But I don't think that all of this is going to take us through all of Friday.
Okay.
I don't think it'll be that hard. Yeah. So we are doing fine. Unless, if there are other questions, I'm happy to entertain them first. I'm not trying to rush us through it.
Oh, no,
I just feel like we've kind of belabored that a little bit and I'm ready to move on. But I don't know if you all are. Are we okay? Let's do capacitors.
Mr. Hobart has giant capacitors in his room.
Yeah.
They're
Big
kinda
scary ones? Yeah. So just to be really clear, when you're looking at the capacitor stuff in your book, There's a little bit from 28, and then most of it's in 29. We've done most of this before, this concept before, so let's just kind of go through what's going on here. So a capacitor is, all we're talking about is generally two plates, metal plates, that are sitting parallel to one another, such that we've separated the charges, and if we've separated the charges, then we know that there's a what between them? Whoa! It all fits together. See how this works? We know, because we derived it, I think, twice last chapter, that the electric field for a capacitor is equal to eta over epsilon naught, right? Okay? Eta being the charge distribution on the plates divided by the permittivity of free space. Okay? So this is the electric field established in a capacitor due to that separation of charges. We know that electric potential energy is equal to Q times E times D. And so we can divide. And we can say that voltage is equal to U divided by Q, which is E times D, or E times S. This distance here is the distance for a capacitor from the negative electrode okay? It may be at ground, it may not, but it's at the lowest possible place we're at, all right? And this is the electric field. So we can use those two statements to throw some things together. What's what?
So is epsilon not like the permittivity of like a vacuum?
Mm-hmm. Yes. So
So
then when we get into dielectrics, then it'll change.
Is it smaller for some dielectrics?
Yes. Yes. And we'll do that on Wednesday.
Okay.
Yes. We're going to talk about dielectrics on Wednesday.
I asked that question a while ago.
Wednesday.
Yeah. Yeah. In class.
Okay.
Yes, in class. All right. So just to kind of put all this stuff together and make sure this is making sense to us, we can draw ourselves a capacitor. We've done this a bunch of times already. Put a bunch of positive charge here, put a bunch of negative charge here, and draw some electric field lines. Go ahead and draw those electric field lines. Where are they going to go? To the right, right? They're just going to go from positive to negative all the time, telling us the direction that a positive charge would move. When we're talking about these things, which side would be at the high potential? The positive side, the left side, that's going to be at high potential. And the other one's going to be at low potential. Sometimes the way that we describe things, instead of saying D here, I'm going to call each of these sides S, and I'm going to say S is equal to 0 here, and S is equal to the distance D across the capacitor there. So at any given point, I can find the voltage, knowing how far away I am, again, from the 0 point, from the negative electrode. Really quick for me, would you draw your equipotential lines inside that capacitor? That should be pretty straightforward, right? What do they look like?
They're parallel to the plates.
Parallel to the plates, equally spaced. Something like this. Equal space between them, which I'm not drawing very well, but that kind of idea. Life is okay? Okay, I'm going to throw a problem at you real quick. I copied it because there was a lot of words and they had some data, and it seemed like it'd be easier to just give it to you. You've got a couple minutes. I want you to start it. We will finish it on Wednesday, but I want you to have started it prior to that. So don't pack up yet.